Good day, everyone. The topic to be discussed by our group is all about the Cauchy distribution. Contents of this video lesson are the following. Number 1, orientation. Number 2, characterization. 2.1, probability density function. 2.2, cumulative distribution function. Number 3, properties. 3.1, why the mean is undefined. 3.2, why the second moment is infinite. And number 4, example.
Cauchy distribution, sometimes called the Lorentz distribution, is named after Augustin Cauchy and Hendrik Lorentz. It is a family of continuous probability distributions which resemble the normal distribution family of curves. While the resemblance is there, it has a taller peak than a normal, and unlike the normal distribution, its fat tails decay much more slowly. The Cauchy distribution is well known for the fact that its expected values and other moments do not exist. The median and mode do exist, and for the Cauchy, they are equal. Together, they tell you where the line of symmetry is. However, the central limit theorem doesn't work for the limiting distribution of the mean. In sum, this distribution behaves so abnormally it's sometimes considered the Hannibal Lecter of distributions. On the other hand, this distribution also has its significance. It is used to describe resonance behavior. It is a popular distribution for robustness studies. It models the ratio of two normal random variables and polar and nonpolar liquids in porous glasses. In quantum mechanics, it models the distribution of energy of an unstable state and collision broadening in spectroscopy.
Cauchy distribution. The Cauchy distribution is a family of continuous probability distributions which resemble the normal distribution family of curves. It has two main parts, a scale parameter and a location parameter. Now let's differentiate the two. First, we have the location parameter XO. It tells us where the peak is, while the scale parameter is half the width of the PDF at half the maximum height. And we're going to know how this each looks like later on. In other words, the location parameter XO shifts the graph along the x-axis, and the scale parameter lambda results in either shorter or taller graph. Now let's take a look on the graph. Does the graph has different curves? Yes, it has. How about the colors? It has what colors? It has red, green, blue, and pink. Now, let's examine the location parameter and the scale parameter. Let's start with the location parameter XO. Remember that the location parameter tells you where the peak is. Now, let's have first the red curve. For the red curve, the peak is a line or adjacent to 0, and it goes the same with the green and blue. How about the pink? For the pink, the peak of the pink curve is aligned to -2. That's why the value of the pink curve is -2 for the location parameter. Now we're done with the location parameter. Let's have the scale parameter. Remember that the scale parameter is half the width of the PDF. So we're talking about the width. Let's start with the red curve. For the red curve, it's 0.5. For the green, it's 1. Blue is 2. Pink is 1. Let's examine the values of the scale parameter. What is the smallest value of the scale parameter? Or which curve has the smallest value of the scale parameter? It's the red curve, which is 0.5. It goes the same with the concept that the smaller the scale parameter, the taller and thinner the curve is. Is it true that the red curve has the tallest and the thinnest curve? Yes, it is. That's why it's true with that concept that the smaller the scale parameter, the taller and thinner the curve is. Now let's take a look with the green curve. For the green curve, the location parameter is 0, while for the scale parameter, it's 1. And it applies a special case of the standard Cauchy distribution that says XO, or the location parameter, which is 0, and the lambda, which is the scale parameter, 1, is the standard Cauchy distribution. For the formula for PDF, you can see it here. It's 1 over pi lambda over x minus xo squared plus lambda squared.
The Cauchy distributions group, I'll be discussing to you its characterization, and at the same time I'll be discussing as well the probability density functions. But before I explain probability density functions, I would like to expound first the word cumulative distributions. As we all know that this one is used to calculate the area under the curve to the left from a point of interest. It is used to evaluate the accumulated probability for continuous probability distributions, and that is the area under the curve, which is equal to 1. And the difference between cumulative distributions and the probability density functions, or the PDF, is it describes the shape of the distributions. I have here some examples like the uniform distributions, exponential distributions, or the normal distributions. I'm gonna go first for the uniform distributions, which is equal to f of x, and that is equal to 1 over b minus a. And if I'm gonna describe the probability density functions, it looks like a rectangle here for the uniform distributions, wherein the highest the highest point is the function of x, and below that will be the distance between a and b, wherein x is in the middle. And what is this? If I'm gonna compute the cumulative distribution functions, the formula will be the area to the left of x. Basically, the area will just be b times h, or that is equal to x minus a times f, the function of x, and that is equal to x minus a times 1 over b minus a, or it is equal to the probability of the capital letter X less than or equal to some number x, which is equal to x minus a over b minus a. Okay, moving forward. Okay, moving forward here for what is this? Okay, for the exponential distributions, I could say that if we're gonna graph the exponential functions, the highest point will be the y-intercept, or equal to lambda, symbol lambda, and it decreases all the time, going down, and that is the probability density function formula is equal to the function of x, which is equal to lambda e raised to the power negative lambda times x, wherein lambda is just equal to 1 over the mean. Okay, and to compute, since the probability density functions is the area to the right, the formula will be 1 minus quantity 1 minus e raised to the power negative lambda x. Simplifying that one, the area will just be equal to e raised to the power negative lambda x. Thank you so much.
The Cauchy distribution is an example of a distribution which has no mean, variance, or higher moments defined. Its mode and median are well defined and both are equal to x sub 0. When u and v are two independent, normally distributed random variables with expected value 0 and variance 1, then the ratio u over v has a standard Cauchy distribution. If x sub 1 to x sub n are independent and identical distributed random variables, each with a standard Cauchy distribution, then the sample mean x sub 1 plus x sub n over n has the same standard Cauchy distribution. The same standard Cauchy distribution, we have the sample median, which is not affected by the extreme values, can be used as a measure of central tendency. The standard Cauchy distribution is T1, and the characteristic function states that let x be defined a Cauchy distributed random variable, and the characteristic function of the Cauchy distribution is given by the formula given.
One of the properties of the Cauchy distribution is that the mean here is undefined. Now, why is the mean undefined? I have read from wikipedia.org that if a probability distribution has a density function f of x, then the mean, if it exists, is given by the integral from negative infinity to positive infinity of x times f of x dx. We may evaluate this two-sided improper integral by computing the sum of two one-sided improper integrals, and that is the integral from a to positive infinity of x times f of x dx plus the integral from negative infinity to a of x times f of x dx for an arbitrary real number a. So, for the integral to exist even as an infinite value, at least one of the terms in this sum should be finite, or both should be infinite and have the same sign. But in the case of the Cauchy distribution, both the terms in this sum are infinite and have opposite sign. Hence, it is undefined, and thus so is the mean. Basically, as per Bale Amadio, the mean of any random variable is the integral with respect to x over the support of the variable of the function x times f of x, where f of x is the variable's probability density function. For the Cauchy, this integral is undefined. The support of a Cauchy random variable is minus infinity to plus infinity. So, the integral representing the mean is an improper integral. The limit of the definite integral x times f of x as the limits of the integration approach minus infinity and plus infinity. The tails of the Cauchy density function are heavy. They approach the x-axis more slowly than, say, the tails of a normal density. And as a result, the limits for the improper integral described above do not exist.
The distribution of horizontal distances at which a line segment tilted at random angle cuts the x-axis. Tangent theta is equal to x over b. Then, to derive the formula, theta is equal to tangent raised to the power of negative 1, which is the inverse of tangent theta, times the x over b. D theta is equal to negative 1 over 1 plus x squared over b times dx over b is equal to negative b dx over b squared plus x squared. D theta over pi is equal to negative 1 over pi times b dx over b squared plus x squared. To integrate, d theta over pi is equal to 1 from negative pi over 2 to positive pi over 2. And to integrate negative infinity from negative infinity to positive infinity of 1 over pi times b dx over b squared plus x squared is equal to 1 over pi times the quantity of tangent theta raised to the power of negative 1 times x over b from negative infinity to positive infinity is equal to 1 over pi times the quantity of 1/2 pi minus 1/2 pi is equal to positive 1.